Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. El-Moursy again, and we are continuing with the digital logic design recordings. And today we are uh, starting chapter number 4, lecture number 17. Chapter number 4, lecture number 17. As the detailed schedule showing, today we will cover what's called the typical DLD design steps. We will learn a new component called the block diagram concept, and we will solve one full example for these kind of problems. We will utilize the slides here a little bit. So actually, the design of the digital logic circuits can be classified into two main categories or two types of circuits. All what we have learned so far is fall into the category that is actually called the combinational logic circuits. Why it is called like that? Because actually the circuit is a combination of circuits of logic gates. Together they are building the whole circuit. So we call it the combinational circuits or the combinational logic circuits. For the combinational logic circuits, this is not the only type of circuits that we have in digital logic design. Inshallah, we will go to chapter number 5. We will learn a different type of circuits called sequential circuits. So combinational circuits are covered in chapter number 4 with the background that we have learned through the three basic first chapters, chapter 1, 2, and 3. We have been prepared with all the basic knowledge that we have to learn, that we have to know in order to build a real life circuits. Now we are shifting to more reality, to the reality of the circuits that are used and utilized extensively in our daily life. And inshallah, when we go to chapter number 5, we will add one extra component, one extra dimension to those circuits. So we are building on top of what we have learned in the whole course. Chapter 5 is built on top of all what we have learned chapter 1, 2, 3, and also chapter 4. So every information here is built on top of the other. So that's why you have to hear the lectures kind of sequentially. So sequential circuits, we will also, inshallah, we will discuss them, inshallah, in chapter 5 and in chapter 6. So chapter 4 will be dedicated to the applications of the combinational circuits based on the knowledge that we have already got. So combinational circuits is nothing but a group of logic gates together with maybe too many inputs or too many outputs or both in order to serve some particular purpose or service in for the an engineering problem that is being solved by the combinational circuits. Combinational circuits actually define or one extra component that we want to learn in digital logic design is what is called the block diagram. As you can see in the slide here, the block diagram is just a box that actually shows the most abstract representation for your circuit. So any combinational circuit will be represented by what we call the block diagram. The block diagram is just a box and it has three components. Component number 1 is the name of the block, which usually indicates what this circuit is doing. I may build a block to build an adder, a subtractor, a comparator, as we will see, multiplexer, demultiplexer. I want to solve maybe the control for an elevator. Okay, each of those problems, if they can be solved by the digital logic design, I can build a block diagram for the problem. The first component is the name of the block, which indicates the functionality of the block, and two other components, group of inputs and group of outputs, as it is shown in the slide here. Okay, so I have group of inputs and a group of outputs. So typically, if I want to solve a digital logic design problem, or if I want to utilize the digital logic design to solve my problem, I usually follow some steps. Okay, these steps may be repeated, may be enhanced, but those steps are what we want to learn today. So now I prefer to go back to our screen, our demonstration on the board, in order to demonstrate to you the concepts in a more clear way. Okay, so now we are discussing chapter number 4 for combinational circuits. If I know that I have a problem and I think that this problem, the digital logic design can provide a solution for the problem, so I have to follow some kind of a standard steps in order to solve the problem using the digital logic design. Those steps is what we will be explaining today. So my first step in solving any problem, the problem usually will be provided to the engineer, to the design engineer, through some paragraph or statements. Somebody have a problem and he is thinking or anticipating or imagining that the digital logic design can provide a solution for the problem. So he will provide to you what we call a word problem. A word problem means he is actually describing the problem to you as an engineer in words. Okay, I want to design blah 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 this inputs that I have. The system should react to the inputs in that way, something like this. So your mission as an engineer, when you receive this word problem, is what we will be listing here. Step number 1 to solve any problem is identifying the inputs and the outputs of the problem. Your first step is to identify where are the inputs of the problem, where are the outputs of the problem. This is step number 1. And from step number 1, you can start building what we call the block diagram. To build block diagram for the problem. Let me just give myself some space here. Building a block diagram. Okay, what's the block diagram? It's just a box, as we just indicated. Since I already identified the inputs of the problem and the outputs of the problem, I can start building my block diagram. Usually, I give a name for my circuit. And the block diagram shows the inputs in one side and the outputs in the other side. This is the block diagram. That's it. Okay. So this is step number 1. During step number 1, you have to first verify if this problem that the digital logic design has a solution for or not. Okay, not any problem in life can be solved by DLD circuits. Okay, so the problem should be suitable for the digital logic. That means, so how can I identify the problem is solvable by DLD or not? It depends on the inputs and outputs. If they are, if they have, okay, a binary relationship, if the inputs are binary, if the outputs are binary, that means I have a binary problem. As long as I have a binary problem, that means the digital logic design have a solution for that. So the DLD can help me to solve the problem. And confirm that inputs and outputs are binary. If the inputs are binary, if the outputs are binary, so that means DLD have a solution for your problem. If not, so you have one of two things. Either there is an easy way to convert or to translate or to represent the inputs and output in a binary format, so you can go ahead with your solution. If you cannot do that, that means this problem is beyond the scope of the digital logic design. DLD design cannot provide a solution for you. Okay? Make sense? But this is step number 1. Identify the inputs and outputs and verify that the inputs and outputs are in binary format. Okay? Then, step number 2. The first thing that you are developing in digital logic design is unlike what we did in chapter 2. In chapter 2, we started to solve the problem by the equation. Okay, we learned so far that the digital logic circuits, the combinational circuits, have 3 major components or 3 major representations. You still remember them? Okay, we have the truth table, TT. We have equation. We have circuit diagram. And today we add to those 3 basic components the block diagram. So we have 4. In chapter 3, okay, we also learned an extra component that assists me to design the circuit efficiently, which was the K-map. Okay, so we have actually 5 components so far. We have the block diagram, we have the truth table, we have the K-map, we have the equations, and we have the circuit diagram. Okay, so what is the, so we started with the block diagram. Then what comes after that? The second component is the design direction. When you design a circuit, the second component that you are seeking is the truth table, TT. You should be able to build a truth table. This is the moment of truth. This is the table of truth. This is the table that actually describe and explain to you the relationship between the inputs and outputs that you have identified in step number 1. If you can build this relationship between the inputs and outputs successfully, that means you can go on with your design. Okay, step number 2 is build TT for the problem. Step number 3, what comes after TT? If I successfully build a truth table for my problem, that means And next is I need to design the circuit. In order to design the circuit, are we seeking a design for the circuit or the best design of the circuit? The best design of the circuit has actually three features. One type of logic, simplified to the minimum number of gates, and has the minimum delay ever. In order to achieve those three goals, I need to simplify the equations for the problem. So I do not want to get equations for the problem. I want the minimum representation or the simplest equation for the problem. And this can only achieve by K-map. You can build K-map for each output. Each output, I build a K-map for the output, simplify using the K-map. Whatever, if the question in particularly indicates to you that you have to use two-level NAND, that means I will simplify using SOP simplification, gathering the ones. If the question asks me I'm looking for a two-level NOR implementation, that means I will simplify using POS, the zeros. So if the question did not give any option, okay, so you are free to use either SOP simplification for the ones or POS simplification for the zeros. Okay, so build the K-map, and from the K-map I will drive what? Get drive equations for the outputs. From the K-maps, I can get the best equation, the minimum equation, set of equations for my problem. Okay, as we learned in chapter 3. Then step number 5 is to draw the circuit diagram for the circuit. So drawing the circuit. So we started in chapter 2 by learning only 3 components. We learned the TT, we learned the equations, we learned the circuit diagram. Okay. In chapter number 3, we added component, the fourth component, which was the K-map, and we learned why we are learning the K-map. Okay, for the simplification. And in this chapter, only one extra step is added, which is the most difficult and the most critical step in your daily design. Okay, because right now you need to translate the English language into a circuit. Okay, in particularly into a TT, which is kind of maybe a little bit challenging. Okay, so accordingly, so once you get that, that means you have all of your circuit is ready and you can ship the circuit. Why is doing this block diagram? Because the circuit that you are building may be just one component in your full design. Very shortly, starting next lecture, we will start building a complicated composite circuits. These circuits, I cannot build the whole circuit as a whole at once. I have to dissect it into smaller blocks, and I want to build each block alone. Okay, when I connect those blocks together, I will get the whole circuit that I am looking for. By the way, we are doing this in our daily life for any other design, not in particularly the daily. Okay, you can imagine when they decide to build the whole university. Do you think that they build the whole university all at once? Definitely not. Basically, what's happening is that you have some drawing or some idea about each department and the department is a group of rooms. And so you make a design for a room, and from the room you can get the floor, and from the floor you can get the building, and from the building you have a department, from the multiple departments building for you a college, and a group of colleges will build the university. So this hierarchical way of design is followed in any engineering design. You cannot build everything at once. So you start with a small basic block, okay, which we call it the block diagram, and you group of block diagrams together will build a bigger circuit or a bigger architecture, okay, and so on. So you can imagine how people like us building the most sophisticated digital logic circuit ever in this earth, which is the microprocessor. Do you imagine that the microprocessor that has millions of transistors, millions of logic gates have been just built at once like that? No. We have small blocks like the blocks that we will build throughout this chapter. And when we gather those blocks together, we will build bigger blocks. And those bigger blocks connected together to build the sub blocks, and then finally I will get the whole design. So this is actually the flow of your work, and we want today to start demonstrating through one example how can I follow these steps in order to build my full circuit. So let's get it started with our first example today, and this example that we will be explaining will take it from our slide notes of the course. Okay, so let me switch back to the share with you our screen here in order to actually basically show you the example that we are about to demonstrate. So in our slides for chapter 4, we have the example in slide number 13, as you can see. As you can see here, we have a word problem, a problem that is being explained to you through an English language. We have to read the problem, we have to reflect on the problem, identify where are my inputs, where are my outputs, are they in the binary format or not? If not, how can I convert them or translate them or represent them in binary? And once I finish that, that means I'm ready to identify or to place the first step or finish the first step of my design. Let me also just erase the steps that we have mentioned here, and let me put kind of a summary for them, okay, on the board in order to allow you to follow the steps that we have learned in a more descriptive way. Let us so while you are reading the problem here, I'm just modifying the board to put the steps, the typical steps for design. So let me just go back to the board in order to show you what we are doing right here. Okay, so the typical steps for design. Number one, as we mentioned, identify in, out, and verify they are binary. Step number two, validity. Step number three, K-map. Step number four, sorry, this is something that we missed here, okay? After this identification, I have to do what? have a block diagram in step number 1. Step 2 is the truth table. Step number 3 is K-map. 4 equations from the K-map. 5 circuit diagram. Okay? Make sense? Okay. Let's go back here. Reading the problem. Let's read the problem. In a daycare, a game called Light the Bulb, Not the Buzzer. So this is the name of the game. Light the bulb, not the buzzer. So accordingly, I can start by my first step, building a block diagram for the problem. I already have got the name of the game. Light bulb, not buzzer. Okay, so this is the name of the game. This is the name of the block. The game is composed of 4 chairs, a light bulb, and a buzzer. So he gave me the basic components of the problem. 4 chairs, light bulb, and a buzzer. The bulb will light if 2 or more children are sitting next to each other. So he gave me a further description, explanation of what is going on or how the inputs and outputs of the problem are interacting with each other. Okay, the bulb will light on if 2 or more children are sitting next to each other. The buzzer will go on if the number of children sitting on the chairs is greater than 1, 2 or more. Design a combinational circuit for the game. Okay, great. So, from the description of the problem, we can identify the following components. We have 4 chairs. We have 1 light bulb. We have 1 buzzer. So let me go back to the screen to show you what we have here on our screen. We have a block diagram with the name of the problem, light the bulb, not the buzzer. Okay, we still want to identify the inputs of the block diagram and the outputs of the block diagram. He actually go ahead with the slides with the description, saying that I have 4 chairs, 1 light bulb, and 1 buzzer. It's easier for me definitely to identify or to represent each input and output through a symbol. So since I have 4 chairs, I will call them C0, C1, C2, C3. Okay. Then I have also the light bulb and I have the buzzer. Let me, for a better utilization of this, let me just redraw that. Okay. So now here we have the 4 chairs. I call them C0, C1, C2, and C3. We have light 1, light bulb. I will call it L. We have also one buzzer. I will call it B. Okay, these are just parametric name to make my work easy in solving the problem. Light bulb, buzzer, and 4 chairs. From the description of the problem, if we go back to the description of the problem, let's see, okay, how he built the relationship between the parameters. The light bulb will light on if 2 or more children are sitting next to each other. The buzzer will go on if the number of children sitting on the chairs is greater than 1. This actually gives me very important information. Right now, I can see, I can understand, I can comprehend from the description of the problem that the light bulb and the buzzer are getting affected by the chairs. So that means which of those parameters are my inputs and which of them are the outputs? Definitely, the light bulb, okay, is getting affected by the chairs, and the buzzer is getting affected by the chairs. So accordingly, I can easily recognize that the chairs are inputs and light bulb and the buzzer are outputs. So in this problem, I have how many inputs? I have 4 chairs. How many outputs? I have 1 light bulb and 1 buzzer. You know what's buzzer? Buzzer is making sound, like the horn of your car. This is the buzzer, something to make sound. The second step, identify the inputs and outputs and verify whether they are binary or not. The light bulb and the buzzer are binary parameters or not? Yes, they are binary. Why they are? Because actually, whether the light bulb or the buzzer, they are go through only 2 states. They can be off, which we can give it the value 0, or they can be on, which we can give it the value 1. If a binary is binary, they are binary. The bulb and the buzzer are binary. But what about the inputs? The chairs. Is the problem actually uh, asking or discussing? Let's go back to the definition of the problem. Okay. From the problem description, what kind of information he mentioned about the chairs? Do I care about the color of the chairs? How luxurious are the chairs? What's the fabric on the chairs? Does they have actually back or not? No, they actually, the chairs are affecting the light bulb and the buzzers in only one sense, whether there is a student sitting on the chair or not. This comes in the description. The bulb will light on if 2 or more children are sitting next to each other. Okay, the buzzer will go on if the number of children sitting on the chairs is greater than 1. If the light bulb, the bulb will go on if the students sitting next to each other, and the buzzer will go on if the number of students sitting on the chairs are greater than 1, 2 or more. So here he actually built the relationship between the light bulb and the buzzer and the inputs and outputs. Before even go to that, first of all, let me ask myself, is the chair, the 4 chairs, binary or not? They are binary, because actually I only care about 2 states of the chair. Either no student, no sit, nobody sit on the chair, we can give this the value 0. Or some students sit on the chair, we can give this the value 1. Okay, so the 4 inputs also have a binary value. Light bulb and the buzzer are affected differently by the chairs. The light bulb will go on if two students sitting next to each other. So there is some geometry here that is missing in the problem. He is actually looking for, okay, what is the orientation of the chairs. So we can have many orientations for the chairs. Okay, the simplest orientation is to just assume that those 4 chairs are in a row: C0, C1, C2, C3. So if I assume the chairs are organized in a row like this, so I can decide for each of those binary value, sit or no sit, whether the students sitting next to each other or not. From this description, after verifying that the inputs are binary, I can go directly to build what? To build the block diagram of the problem. The block diagram of the problem will show the inputs. I have 4 inputs: C0, C1, C2, and C3. I can see 2 outputs: light bulb and buzzer. And here I have the name of the block: light bulb, not buzzer. This is how they name the game. Okay, so now I achieved the first component of my design, which is verifying the inputs and outputs and building a block diagram for the problem. Step number 2 is to go directly to the truth table. Okay, and this is a huge truth table. The truth table here should carry the information of the relationship between the inputs and the outputs. How many inputs in the problem? I have 4 different inputs. How many outputs of the problem? I have 2 outputs. So accordingly, I have 4 inputs, which are the chairs. Okay, if we even follow the order here, so we have chair C. Let's order them chronologically, similar to what we have on the TT, which may be more reasonable. So let's call this C0, C1, C2, and C3. So accordingly, here I have C0, C1, C2, C3. These are the inputs. And I have also the outputs. And the outputs are L and B, the light bulb and the buzzer. Okay? Now, the second question that I have to ask myself: how many rows in my TT? So the TT contains how many columns? The TT has number of inputs and number of output columns. So it has 4 inputs for 4 columns for the inputs and 2 columns for the outputs. How many rows? How many rows? The golden rule is 2 to the power a number of inputs. 2 to the power number of inputs. That means how many rows here for this problem? 16 different rows. I have 16 different rows in my TT. Can I fill in the TT? Yes, for sure. I have 4 inputs: 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Then 4 zeros, 4 ones, 4 zeros, 4 ones. Finally, 8 zeros and 8 ones. Great. We can also put here the designator. The designator is just chronologically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay? All right. Now, from the relationship that he mentions between the light bulb and the chairs, so L, which is the light bulb, will go on if 2 or more students sitting next to each other, as the problem explained. Go back to the slides if you would like to confirm that. So, since we give the value 0 for no student sitting on the chairs, 1 for a student sitting on the chairs, we can easily identify whether 2 students sitting next to each other or not. Okay? So, based on this definition, all here means no student sitting on the chairs. That means L should be 0. Here I have only 1 student sitting on the chairs. Here I have also 0. Okay? Here also 1 student in the second chair. 0. Here I have 2 students sitting next to each other. The chair 0, 1, chair 1, 1. And they are next to each other, as this organization shows. It means the light bulb should be on. Here, only 1 student in chair 2, give a 0. Here, 2 students sitting on the chairs, but they are not next to each other. In the case number 5 here, 1, 0, 1, 0 means they have separated by at least 1 chair. So the light bulb should go off. Here is 2 students sitting next to each other. Here I have to put I have to put 1. Here, 3 students sitting next to each other, 1. Here, only 1 student, the last chair, 0. Here, 2 students, but are far from each other, 0. 0. 1. 1. 1. 1. 1. Okay, so we can fill in the truth table based on the definition of the problem. This is for the first parameter or the first output, which is the light bulb. Going to the next one, which is the buzzer. The buzzer is defined as the buzzer will be lights on or if 2 or more students sitting on the chairs. Okay, if you want us to go back to the definition, we can. Let us just verify that. I'm just reviewing with you the description that is given in the problem. You see here, okay? So the bulb will light if 2 or more children are sitting next to each other, which we already saw. The buzzer will go on if the number of children sitting on the chairs is greater than 1. Either 2 students or more, we have to consider that. Okay, problem So let's go back to our screen here to see how this will be done. Okay, so for the bulb, I here looking for the chairs themselves and how they are organized, or I'm looking for the total number of students sitting on the chairs. I look on the total number of students sitting on the chairs. So to assist me doing that, I have added this column to actually count the number of students sitting on the chairs in each case. In this case, 0 students sitting. In the first one, in this one, I have 1, 0, 0, 0 means 1 student sitting on the chair. 0, 1, 0, 0 means also 1 student. 1, 1, 0, 0 means 2 students. 0, 0, 1, 0 means 1 student. 1, 0, 1, 0 means 2 students. Then 0, 1, 1, 0 means 2 students as well. 1, 1, 1, 1, 1, 1, 0 means 3 students. 0, 0, 0, 1 means 1 student. 1, 0, 0, 1 means 2. 0, 1, 0, 1 means 2. 1, 1, 0, 1 means 3. 0, 0, 1, 1 means 2. 1, 0, 1, 1 means 3. 0, 1, 1, 1, 1 means 3. And finally, I have the 4 students sitting on the chairs. So this way, I count the number of students, so I can reflect on me. If this number is beyond 1, 0, beyond 1 means 2 or more, that means the B should be 1. If 0 students sitting on the chairs, B should be 0. 0, 0. Here is 2 students, means 1. 1 student, 0. 2 students means 1. 2 students means 1. 3, 1. 1 student, 0. 2 students, 1. 1, 1, 1. All of the rest should be 1s. So I succeeded to get the second component, which is the truth table of the problem. Great, makes sense? Now, the next step is, in order to design this, I need a map. To simplify, I need the minimum equation for my problem. The problem has how many outputs? 2 outputs. If I have to have how many K-maps? A K-map per output. If a K-map for L and K-map for B. If I have 2 K-maps. Each of those K-map, what's the size of the K-map? Size of the K-map depends on the number of inputs. I have 4 inputs in the problem. That means the K-map should be of 4 inputs. If I 2 K-maps, each of them is 4 inputs, is what I have to build here. Okay? So let's just build a K-map for one of the inputs. Okay? Can we build the K-map for L? The answer is yes. And the K-map will be a 4-variable K-map. Big K-map. Okay? So let me just draw the K-map here. K-map for 4 variables. You already have learned that in the tutorial. So this is K-map for the output L. You have to watch while you are building the K-map. You have to watch for what? You have to watch for the order of the parameters. The first parameter here, so the order of the parameters should match between the TT and the K-map. The component is actually component number 2, which is TT. Now we are deriving component number 3, which is the K-map. Okay? So the first parameter here, the most significant parameter here is the one that you have to draw here in that side. So I have here C3 bar, C3. The next one, which is C2, should be opposite to it. So to this one, you get C2, C2 bar, C2 bar. Then I have C1, so I have C1 here. So C1 bar, C1. Finally, I have to have the C0 here, so C0 bar, C0 bar. Okay. Mapping from the TT to the K-map, also you have to pay attention to that. However, maybe it's better for us to take a little bit of break and then we will continue with the next part. We will map the functions from the TT to the K-map. We will simplify and we will see how we will proceed with the rest of the steps, inshallah, in our next part of lecture 17. So let's take a little bit of break. Thank you.